Hey guys, welcome to the lesson for section 2.1, Properties of Exponents. Exponents are really useful tools that we have in mathematics all over the place and lots of different types of functions. And so we want to talk about what they are, what they mean, and how to work with them before we start to get into those functions. So the first thing we need to do is get a base definition of what it means for something to be an exponent, what an exponent does, what it is. So we say that for any real number, b, and natural number n. So b is just any real number, so any number we want as long as it's not an imaginary complex number. And n is a natural number. So natural numbers are our counting numbers, that is our 0, 1, 2, 3, 4, 5, all the way up. So not negatives, just 0 up. Okay? So for any real number b and natural number n, we say that b to the n is the product of b times b times b, continue doing that, times b, n times. Okay? So any real number raised to this power means that we multiply it by itself that many times. And so to get some definition, some vocab for us, so b to the n, we call this the base. So the b is the base of our exponent. Okay, n is our exponent itself. Okay, and we call this whole thing, we'd say that this whole thing, that the entire thing is a power of b. Okay, so let's get a more specific example going here, right, without some of these variables. Let's say we've got, let's go easy with ourselves, 2 to the third power. Okay? So by the definition, what this means is I need to multiply the base 2 times itself 3 times. So this is just 2 times 2 times 2. Okay? And that is a lovely, that's 6, sorry. Very common mistake, right? That's a bad thing to do, multiply these. 2 times 2 is 4. 4 times 2 is 8. Okay? So, this is our very basic thing. So what we would say here, there's a lot of things we can say, right? We can say that 8 is a power of 2. Okay? A little nicer. We could say specifically that 8 is the third power of 2. Okay? So when you hear things like, is it a power of 5? Right? So is 125 a power of 5? What that means, what they're asking is, can 125 be written as 5 raised to some power? So here, 8 can be written as 2 to the third power. In other words, these two things are equal. That means that 8 is the third power of 2, or 8 is a power of 2. Okay? Now let's think of some other rules that we might have. And I want to do this with a nice specific example, and then we'll build into the actual definition. So what if I have something like 3 squared times 3 to the 4th. What can I do with that? Well, right now, what we can do is we use our basic definition of what those things mean. So 3 squared is just 3 times 3. So I'm going to put parentheses around this. So that's our first piece. And our next piece is 3 to the 4th. So we have 3 times 3 times 3 times 3. So again, I'm going to put that in parentheses to kind of group these together. So I have my 3 squared and my 3 to the 4th. But I just have 3 times 3 times 3 times 3 times 3 times 3. So I don't need parentheses, right? Because parentheses tell me I have to do this first and this first. But we know multiplication, it doesn't matter what order we do it in. So I can actually just write this as 3 times 3 times 3 times 3 times 3 times 3. Okay, well, we know what that is. That's the definition of exponents, right? that's just 3 to the 1, 2, 3, 4, 5, 6. That's 3 to the 6th power. So 3 squared times 3 to the 4th just becomes 3 to the 6th. So how do I get there? Well, very simply, we just added these exponents, and that's our rule. And it's called the product rule of exponents. And it simply says, if we have b to the n, let me make sure I'm using the same letters as your book. So b to the m times b to the n. So I have some base raised to a power times that same base raised to another power. And those two numbers could be the same thing or not, right? But we could just say that, they're two exponents. The big key here is that the bases are the same. So if those things are there, then we can write this as b to the m plus n. So we can combine those exponents. Now you may be thinking, like, how is that much simpler? Well, if we know what m and n are, then we add them and they're a single number, so then we basically cut our stuff in half, right? Still the same equivalent number, but different. All right. So that's the product rule. Let's talk about another rule. And for this one, let's say we have 5 to the 4th divided by 5 squared. So yes, I'm using 4 and 2. I also don't want to write things out 15 different times, so I'm not going to do 5 to the 15th. So now we have division. So before we had multiplication, now we have division. And so I want to look at this and think, okay, what can I do with this? How can I simplify? Well, let's just, product rule, we can't apply that, right? We don't have any multiplication. So we're just going to stick with our basic definition of exponents, which that says that this numerator, 5 to the 4th, becomes 5 times 5 times 5 times 5. And our denominator, 5 squared, becomes 5 times 5. Now I'm looking at this and I'm going, okay, cool, how can I simplify this? Well, if you remember, if our fraction is all multiplication on top and bottom, there's no addition or subtraction mixed in, we can cancel out common factors. So since all of this is multiplication, I can cancel out common factors. In other words, I can actually cancel out these and these. And what that gives me is I have 5 times 5 in the numerator, so 5 times 5, and there's nothing left in the denominator. And now when there's nothing left in a fraction, we don't put 0, right? What we think is, okay, well, I could really say this is times 1, and so I really have a 1 in that denominator, okay? And so I have 5 times 5 over 1. We divide by 1, or have a fraction over 1, that just doesn't do anything, right? So this is really just the 5 times 5, which is just 5 squared. Now, the numbers may be confusing. You may be like, oh, so we just take this bottom one and make that it? No, that's not what happens. What happened was we subtracted this denominator, the power in the denominator, from the power in the numerator. And so our rule becomes, if we have b to the m over b to the n. Again, very important that we recognize that these are the same base. Okay? So if we have that same base and they're dividing, b to the m minus n. And this is called the quotient rule of exponents. Okay? So quotient division. So if we are dividing a base raised to a power by that same base raised to another power, we can combine those exponents by simply subtracting the denominator from the numerator. Okay? It's pretty nice, right? Now, I want you to remember this trick right here. This kind of, when everything's gone, there's still a 1. Because that brings us to another really kind of weird situation. Five to the 0. What is 5 to the 0? Well, there's a few ways we can go about kind of showing what this is. One way is to think, okay, the definition of exponents. So it's 5 times itself that many times. How do I multiply 5 by itself 0 times? I mean, there's no 5s, but it can just be nothing, so there must be that kind of 1 there. And that's kind of a really kind of like, it is. But let's use that quotient rule to figure this out, okay? So what if I have 5 to the 7th divided by 5 to the 7th? So first off, if I have something divided by itself, what does that equal? Right? Anything divided by itself, as long as it's not 0 divided by 0, anything divided by itself is always equal to 1. But I can also use the quotient rule we just talked about, and I can simplify this. And to do that, it just means, since the base is the same, we take our base, and we raise it. The power is the numerator minus the denominator. And 7 minus 7 is 0. That's pretty cool. So, this brings us to a really nice little fact that for any non-zero real number b to the 0 equals 1. That's pretty cool. So if we raise anything to the 0th power, it's always 1. Always. All right. Now, there's a couple more rules. There's 2 rules and 3 more rules in particular that I want to really cover with you guys. Well, there's actually 4 more, but forget it. So, this next rule is the power rule of exponents. Okay, and what I want to do is I want to very simply do it with a nice example, and then we'll put it into a general context. So if I have, say, 3 to the 4th squared. Well, this is really a kind of cautious thing that we need to do, and we need to remember our order of operations. Okay, we need to deal with whatever's inside the parentheses, then we kind of work our way out, right? But in this case, I'm not going to. I know I just said we need to worry about our order of operations, but I'm not going to here. And the reason why is because I'm just rewriting. I'm not simplifying or evaluating. Or I'm not evaluating. I'm just kind of rewriting and simplifying. So what I want to think is, what does it mean to have something squared? So I no longer have b squared, where b is just a number. My b is now this expression 3 to the 4th. So let's evaluate that squared first. So that just means take this base and multiply it by itself. So this becomes 3 to the 4th times 3 to the 4th. Because I just take this base and multiply it by itself twice. Well, this looks exactly like the product rule, which says if I have the base to a power times that same base to a power, we just add those exponents, right? Okay, so this just becomes 3 to the 4 plus 4, which is 3 to the 8th. So how can I get from 3 to the 4th to the 2nd to 3 to the 8th? And that's right, we just multiply these guys. It's just a repeated application of the product rule. So our power rule of exponents becomes very simply, if I have some base to a power, and then that whole thing is raised to another power, we multiply their exponents together. Pretty easy. So the product rule says if I have a base to a power times that same base to a power, we add the exponents. The quotient rule says if I have a base to a power divided by that same base to another power, I can subtract the exponents. And the power rule says if I have a base to a power, I can multiply those exponents. It's pretty nice. All right. Now, what if I have multiple bases going on? So let's look at that. So let's look at, what if I have, say, b times c to the n. Well, it's a big general thing. Let's get a specific example to figure this out. What if I have, say, 3 times 4 cubed. I don't want to write too much. So, I mean, I could multiply 3 times 4 and say this is 12 to the third, and that's absolutely correct. But I want to kind of use this to kind of figure out what happens here. So if I don't know what those numbers are, or one of them is a variable, what can I do? Well, what I can do is I can use the fact that I have, this is my base, right? 3 times 4, which is just 12. So 12 to the third, which is 12 times 12 times 12, right? But in this case, I'm going to write it instead of 12, I'm going to say 3 times 4. So this becomes 3 times 4 times 3 times 4 times 3 times 4. Cool. I have all these parentheses, but I have just multiplication, which we know multiplication can be in any order, so I don't need those parentheses. And furthermore, multiplication, just as I said, can be done in any order, so I can rearrange these. So I could rewrite this 3 times 3 times 3 times 4 times 4 times 4. Hey, that looks, we know what that is. That is 3 to the third times 4 to the third. All right. So what happens here is if I have two numbers, the product of two things, all raised to a power, that's very important. Product. If this is addition or subtraction, this does not work. Only if it is the product of two things can I do this. Okay? If we have the product of two numbers raised to a power, I can rewrite that as each part raised to that power. I can distribute that exponent. Again, only if it's a product, not if it is addition or subtraction. Only if a product. Okay? Now, what's really cool is we get a very simple kind of analogous result if we consider the division or quotient, right? And this is something that you may remember reaching far back into your brain. Division is really just multiplication by the reciprocal, so this is really just kind of an application of this. And so what we end up with is very simply, if I have the quotient of two things to a power, I can again distribute that power. Okay? Pretty nice and easy. So there's some rules. So what I want to do right now is I'm going to rewrite all of our rules kind of over here, really nice and kind of succinct, as easily as I can. And then let's do an example. So I might erase this now too. So we have our basic definition, the b to the n to b. We have b to the n, b to the n. Okay, so over here I've got all of our things down, right? We've got our basic definition of the exponent rule, we've got our product rule, we've got our quotient rule, we have that nice little result that anything to the 0 is 1, we have our power rule, and then we have the two different things but all to the same power, and it all works. Okay, so let's talk about what it means to simplify an expression. So I'm going to write an expression out and we're going to talk about what things we have to do so that it's actually simplified. Okay? So let's look at something nice and crazy. Okay. I want to simplify this expression. What does that mean? To simplify an expression, there's some very kind of simple steps that you have to take. There's some very kind of simple actions you must do. Okay? So to have this simplified means we need to have no parentheses. So this is simplifying. So to simplify, we need no parentheses. Okay? We need that each variable occurs as the base as few times as possible. Now, for the most part, that is going to mean once. That variable should only ever occur one time. In other words, if we have something like where we have this, we would use the product rule to make it so that base only occurs once. There's rare examples where it might have to occur more than once. It's usually with groupings and things like that. But for the most part in this class, it will always be it needs to get down to a one-time occurrence. All numeric values are calculated. In other words, we don't have anything written as like 2 to the 5th or 3 to the 80th. We use our calculators if we need to, and we figure out what that value actually is. So we have something like 2 to the 5th, okay? We actually write 32, not 2 to the 5th, okay? And lastly, all exponents are positive. I will talk about what to do with negative exponents here in just a minute. I want to go through some examples using just these before we introduce that ruling. So let's simplify this expression so that all of these conditions are met. Now, there's a lot of ways we can go about this. You can follow order of operations, just work inside the parentheses, and then we kind of move our way out. This problem here is a nice one because it's a fairly simple one. The inside the parentheses are as simple as it gets. I can't simplify that any further. So what I need to do is I need to use this rule here, the b times c to the m equals b to the m times c to the m. Now, here it says, oh, well, it's only two things, but that's just because two things. I can expand that to the product of as many things as I want. So here, the products I have are 2 times b cubed times c to the 6th. So what I can do is I can rewrite this. And so when I rewrite this, I like to kind of keep parentheses in there so that I'm very clear in what's happening. So I like to use parentheses so I know I'm raising 2 to the 4th power, okay, and I'm raising b cubed to the 4th power, not raising b to the 34th power, okay? So I want to make sure it just makes things a lot easier. So now we want to go through and simplify things as we go. And we can just kind of start left to right. If you want to jump with the variables, use rules first, whatever works for you. There really isn't a right or wrong way as far as like kind of what order to do these in, as long as, because it's all multiplication, right? Multiplication can be done in any order, as long as you're just kind of careful and following the right rules. So let's just go left to right. So 2 to the 4th power, what is that? Well, I'm not going to write it out, but by the definition, that means it's 2 times 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So this becomes 16. Now if you want to, you could just rewrite these and then kind of do a next step, but I'm just going to do this just kind of all at one point, just using these rules as best we can. So if I have b to the 3rd to the 4th, if I look at my rules, which one does that look like? Right, that looks like the power rule, right? I have the base raised to a power raised to a power. So to combine those exponents, I multiply them together. So in this case, what we end up with is b to the 3 times 4. And 3 times 4 is 12. And over here we get the same thing again, right? We have a base to a power, so again we use power rules, we multiply our exponents. So I end up with c to the 6 times 4, which is 24. And that's it. So I have no parentheses, okay? All the variables occur as a base as few as possible, in this case once. All numeric values are calculated, and all of my exponents are positive. This is done, we are simplified. Awesome job. Now let's jump into a problem that's a little more complicated. Why? Because it's fun. Okay. So, I want you to take a minute and simplify this. Pause the video and simplify this yourself. Oh, wait. All right, welcome back. So, what'd you get? Cool. Let's get it together. So, we have to get rid of any parentheses. We have to write the bases as few as possible. We have to calculate all our numerical values, and we have to write all of our exponents as positive. Okay, parentheses. There are none. Cool, done. Next, write our bases as few as possible. So when I look at this, I can really, everything is multiplied, so I can really isolate kind of any two things I want. So I want to isolate these two things first. So I'm going to leave my 4 and my 20 there. I'm still going to leave my c to the 9th and my c to the 5th there. Write that 5 a little better. But I want to deal with this b to the 8th divided by b to the 7th. Because it's all multiplication and division, so we can isolate those. What rule does that look like it applies to? Okay, the quotient rule. So all we're going to do is simply take the exponent in the numerator and subtract the exponent of the denominator. So that gives me b to the 8 minus 7, just b to the first. Now, b to the first power, or anything to the first power, is just that thing multiplied by itself one time, so it's just that thing. So we don't actually have to write that exponent, because technically 4 is 4 to the first power. Right? Anything by itself is just that thing to the first power. So in our next word, we won't write that. So now I want to isolate the c's. 4, 20, I've got a b. Again, right, I don't need to write the power because it's a 1, so it's not a big deal. Again, I want to use that quotient rule, so I take the exponent in my numerator, subtract the exponent from my denominator. So 9 minus 5 gives me 4. So I end up with c to the 4th. Okay. So now, the last thing I have to do is calculate my numeric value. So what's 4 divided by 20? Well, that doesn't work in a whole number sense, but it gives us a nice fraction. We can simplify that. And what we end up with is 1/5. So our final answer is b times c to the 4th over 5. Okay? That's it. It's pretty easy. Okay? So, that is a really simple example, a couple simple examples of simplifying using our exponent properties. I want to talk about one more new property, and then we're going to do some more examples together. Okay? So what I want to talk about is, what happens if I have b to the negative n. So I have this base raised to a negative exponent. Remember, our exponents are natural numbers, 0, 1, 2, 3, 4, 5. So if I have a negative, n is still that natural number, but now it's made negative. How do I deal with this? Well, we're going to use some tricks to kind of figure this out. I want to make this look like something over here. Because if it looks like something over here, I can work with it, right? All right. So, well, I have subtraction, right? And there's a subtraction. So let's rewrite this as a subtraction. So or the exponent as subtraction. So how do I get negative n? Well, easiest way is 0 minus n, right? Because I don't know what n is, so I can't say like, if n was negative 2, I could say, oh, well, that's 3 minus 5. But I don't know what n is, so I can't say it's x minus z. But I can say that it's always 0 minus n. Now this looks like this end of the quotient rule. Now one thing I want to make a point of with all of these, they're equal, which means that we can go from one side to the other. It's not only going from here to here, we can also go backwards. And that's what I want to do here. So if I have b to the m minus n, that means I really have b to the m divided by b to the n. So here I have b to the 0 minus n, so I can rewrite this as b to the 0 over b to the n. Do I know anything about either of those two? B to the n, well, it's just, repeatedly multiplying b, but that doesn't tell me anything new. What's b to the 0? Ooh, that's 1. So this is just 1 over b to the n. And that's our rule. That is the rule for a negative exponent. If I have something raised to a negative power, what we do is we rewrite it. We rewrite it, and one of the things we say is we flip it. Okay? And the reason why I like flipping in terms of when we're thinking about simplifying, because if it's in the numerator, it flips to the denominator. If it's in the denominator, it flips to the numerator. So right now this is in the numerator. So it flips to the denominator, and the exponent becomes positive. Now what's up in the numerator? Well, there's nothing left, but there's always something left, and that something is 1. All right, that's not too bad, right? So anytime we apply a negative exponent, which is whatever it's applying to, flips, okay? If you want to think of that a little more clearly here, we can almost think of this as b to the negative n over 1. So that flipped, and my exponent then became positive, okay? So I've got a very little bit of room here, so I'm going to add that in. B to the negative n, 1 over b to the n. Let's do some more examples. Let's get a little crazy with it. Yeah. All right. I want to simplify this expression. Okay, so we need to get rid of our parentheses, write our bases as few as times possible, calculate our numeric values, have positive exponents. Those are the 4 things we need to do. There's a lot of different ways you can do that here, okay? You could distribute right now to combine like terms to get rid of those parentheses. You could evaluate each one inside its parentheses and then combine things. You could get rid of the negatives. You could do a lot of different things. What I want to do first is I want to multiply these together. In other words, because this is all multiplication, this is negative 2 times a cubed times b to the negative 1 times 5 times a to the negative 2 times b squared. Since this is all multiplication, I don't actually need those parentheses. And I also can reorder these however I want. So what I'm going to do is I'm going to reorder these so that I have like things together. And so I end up with, because it's a negative, I'm going to keep that parenthesis. I have negative 2 times 5 times a cubed times a to the negative 2 times b to the negative 1 times b squared. So all I've done is I've just reordered these things. Because it's all multiplication here, there's no division, there's no addition, there's no subtraction, it's all multiplication. I can reorder it however I want, and I just reordered it so that the like things were together. Makes my life easier, makes your life easier, makes everything easier. So the first thing I want to do is I just want to move left to right. So what's negative 2 times 5? Well, negative 2 times 5 is negative 10. Okay? Now I have a cubed times a to the negative 2. Now you may be thinking, oh, let's use our new rule here because that says that if I have a negative exponent, I move it to the denominator. But let's slow our horses. Let's not get fractions introduced or flip things around and get things crazy unless we have to. I have the same base raised to a power times the same base raised to a power. That's very simply our product rule, which means I add my exponents together. Now, I'm going to write this off. I'm going to write this off on the side. So what I end up with is a cubed plus negative 2. So what is 3 plus negative 2? If we add a negative, that's the same subtraction, right? So we really just have 3 minus 2, so this becomes just a to the first, or just a. Okay, make sense? Now I have a positive exponent. I don't need to worry about using this negative exponent rule. I do the same thing with my b's. Here so I have b to the negative first times b squared, which means what I have is b to the negative 1 plus 2. Negative 1 plus 2 is again 1, so we just have times b. So this crazy looking thing here actually is just negative 10ab. Really simple. And so by following these rules, just kind of going through and doing it, it's really easy. Okay? Let's do another example. All right. In our last example, we're going to work. It's going to be a beast. We're going to work it. We're going to do it. We're going to handle it. Okay? Quick note. This is not the case in this problem, but if you were to say, if this was raised to the negative third power, what you can do is really easy, is just flip this entire thing, and that becomes positive 3. So let's just say, for example, I have something like, say, 2x over 3y to the negative 2. I can just rewrite this as 3y, 2x to the positive 2. So I flipped that fraction, and it became positive. That's a nice way we can apply negative 2 at a whole piece and not have to like distribute all of it and then kind of go from there. So there's a lot of things we can do here. One of the things that we can do is simplify everything as much as we can and then deal with our 3, or we can distribute our 3. Now, what we actually have going on here is a combination of both of these two situations. We have the product of things in the numerator and in the denominator, and we also have the quotient of things. But both say we can just distribute those exponents. So I could really write this as 3 to the third power times b to the negative fifth to the third power times c to the fourth to the third power divided by b to the third power times c to the third power times d to the 10th to the third power. I can distribute that 3 to every piece and get rid of these parentheses. But that's a lot of messy stuff and a lot of things going on. So what I want to do is I actually want to focus on just the inside and simplify that as much as possible. So the first thing I got, if I'm looking at this, I have a 3. There's no other 3. There's no other numbers. So that's just going to stay as is. Now from here I want to isolate things. So to isolate things, right, I have my b's, I have my c's, and then I have a d by itself. So let's focus on the b's. So I have b to the negative fifth divided by b to the third. What that says, so that's a quotient. So quotient rule says to subtract those. So I get b to the negative fifth minus 3. So b to the negative fifth minus 3. And that becomes b to the negative eighth. So I get b to the negative eighth. Now you may be wondering why I'm not dealing with that negative. I'm just taking this one step at a time. If you're somebody who's really comfortable with kind of multitasking in their mental math and want to jump those steps, That's absolutely fine. I'm not going to mark you down. So we got our b's. Let's look at our c's. I have c to the fourth divided by c to the first. Well, that's just classic quotient rule, right? Both are positive. 4 minus 1 is 3. So we end up with c cubed. And I have a d to the 10th in the denominator. This is all still to the third power. So what I've done is, so far, all I've done is made it so all my variables occur as least as possible, as few times as possible. So now I want to simplify this. And there's a few ways I can do that. Again, I could distribute my exponent, or I could get rid of my negatives. All my numerical values are calculated, my variables occur as least as possible, so my options are really to get rid of the parentheses or get rid of negative exponents. I'm going to get rid of negative exponents because I don't like negatives if I can. So I have this b to the negative 8. Remember, a negative exponent, practically speaking, just means flip it. So it's in the top, so it flips to the bottom. And so what I end up with is 3, I no longer have a b in the top, times c cubed, divided by b, now it's not going to be to the negative 8th, because I flipped it, now it's back to positive 8, and I have a d to the 10th. And this is all cubed. So now our last thing, we need to get rid of that parenthesis, we need to get rid of that 3, so we need to distribute it. So what we end up with is 3 cubed times c cubed to the third times b to the 8th to the third times d to the 10th to the third. Okay, you're like, well, we got rid of one parenthesis, but we added 3 more, but we just have to simplify those using our lovely power rule. And we also have to calculate our numeric value now. So, erase that. 3 to the third. So 3 squared is 9. 9 times 3 is 27. So we end up with 27. C to the third. So that's, again, a classic power rule. So we just multiply those exponents. And 3 times 3 is 9. So we get c to the 9th. Okay. Now in the denominator we have b to the 8th to the third. So again, we're just going to multiply those exponents. 8 times 3 is 24. So we get b to the 24th. And lastly, we have d to the 10th to the third. So we're going to multiply those. 10 times 3 is 30. So we get d to the 30th. And there is our simplified statement. So we went from this thing to this thing. And you may be going like, that doesn't look simpler, but mathematically speaking, it's simplified. So that's it for the properties of exponents. There's one more little bit in this lesson that I'm going to cover with you guys because there was kind of no other place to put it, so we're going to put it here. And that's scientific notation. So, tune in for our next little video that is a continuation of 2.1 on scientific notation. All right, guys.